should have the camera running soon, hopefully. Maybe they'll put on the...
Yes, we are in the 74. Actually, we are in the correct one. No?
Okay.
In 73.
Good. Test mic 73. Test mic 73. There you go. So, there you go. Yeah, you might wanna. I'm gonna mute that.
Thank you.
And here you go.
Thank you very much. Yeah, I know. So. Hello. Can you hear me here decently enough? People who are online? Thank you, Kevin. So sorry for this delay. We were having some issues with the audio. So today is the fourth session in performance engineering in this course, the fourth and last. And today we will see how to model the performance using the UML language. Some of you asked me also last day about the motivation of doing this performance engineering. So maybe it's not completely clear, and I will revisit it as well. So the systems we will develop during our careers will have performance requirements. So the clients expect that the system has some good performance. So we can get like the system shall be fast, or some activity in the system shall allow many concurrent users. Then we can get also some information about properties, like some activity X executes slow, and some activity Y executes rarely. Now you know that here there is something wrong, right? So if there are requirements, there has to be possible to validate them. And how should we validate the fast? So we need some detail. So we cannot accept as requirement the system shall be fast, but we can accept as requirement the electronic payment shall be complete in less than 30 seconds in average. Or instead of the system shall allow many concurrent users, we can accept that the system will execute 100 concurrent requests and then see if it saturates or if it still can answer in the response time, in the expected response time. For the properties of the activities, executes slow, maybe we can define like requires 300 milliseconds of CPU time, and some activity that executes rarely, we can define it in our model like not rarely because it's too ambiguous. Like executes the 5% of times that users request the system. So 1 out of 20 we want to execute activity Y. So after having this information, and you have seen also the requirements engineering part, you can elicit the requirements, you can specify these things. But there is not anything that you can do so far during the design with this information. So you have specified the performance requirements. Then during the design and development of the system, you ignore them. Then when the system is coded, the code is available, when you are testing it or operating it, you hope that the performance requirements are satisfied, but in practice you didn't do anything to meet them. You just specify it and then hope for the best. And if the performance requirements are not satisfied, so the system has less performance than required, we need to redesign, renegotiate, and we will have waste a lot of effort in developing the system and testing and maybe even deploying, and we have to restart. So during these sessions, we try to avoid this part. So we have specified performance requirements, and during the design of the system, we try to do as many activities as we can to arrive to develop the system, keeping in mind the performance properties, and to arrive to the testing. We cannot be sure because we are making assumptions, but at least we can arrive with some confidence that we have developed the system based on some evidences, and we have taken into account the performance requirements and the performance properties to develop our system. We can still fail in the testing, so the system can be still lower, maybe because we assume in the specification that there would be less users, and then in reality there are more, or that some activity, some external call could be, we assume that it was faster, and then it becomes slower, or some mutual exclusion, some activities in mutual exclusion that we didn't consider them in the design, and then they were developed, they were implemented like that. But at least we don't arrive completely clueless about having performance requirements, ignoring them, and then let's see if we meet this. So these 4 sessions are to improve this ignoring part. So far we know how to, from the system specification, how to create a queuing network that allows to know performance information about the system, and how to use operational laws that also allow to get some performance indices of the system, very general, and we show how to use the operational laws to get some information that we could put inside a queuing network, and then we get more advanced performance metrics. And today we are going to see how to represent the specification of the performance properties to the design of our system. So assuming that we are designing using UML. So why are we using UML? UML is the de facto standard for specifying and designing software. Many people understand UML. If during the development you are the part of the software engineering and it's a complex system that you may even have dedicated performance engineers, who are using their queuing network language or another one or mathematical formula, and there are also the system, the operators that will take care of the deployment. So each subgroup will have their specialized languages with which they feel more comfortable, but to interact among them, they need some language that all of them understand. And so far, UML was proposed as to unify the modeling, and almost everybody who lives a computer science degree knows UML, can create and understand UML, even created by another community. UML has a rich graphical notation, so it allows us to create many things using the plain UML, the standard one, and it's easy to see and understand what we see. The diagrams are not only focused to a phase of the development, but they can be reused along the whole software process, from the requirements elicitation to the deployment of the system and even maintenance. UML is not restricted to a development paradigm, so if somebody is using the waterfall paradigm or others are using Agile, UML was not proposed only focusing on one of these paradigms, but is general, so even groups that are working with different paradigms and they have also their specific language to work among themselves, that maybe they can find that is more efficient to communicate with the other groups, they need some common language. And there is another characteristic that is going to be quite useful for us today, and it's of UML, and is that if the UML characteristics are not enough, it is extensible. So UML has, inside itself, has mechanisms to extend its own language. We are going to see now why this extension is useful. This is the same example as the same running example we are using during all the sessions. So the 3-layer system. So the document repository, the company that has the users connect via web to a web server, and there are 400 users in the company. The web server receives the user request and communicates to an application server, and the application server processes the document, extracts some data, and then stores in the database server. From this specification, we could create UML diagrams. Do you know the names? Or sequence diagram, activity diagram. So it shows the workflow that the execution starts here and then goes to a process submission activity that is in the web server swimline. Well, here is a partition, and then it goes, when it finishes, it goes to the application server and then to the database, and then it finishes. So with this modeling, we have been able to represent this part of the specification, this part of the web server receives user request, the user connects via web to a web server. We have not specified that there are 400, because we don't know how to put that there are 400 users using the UML notation. And when we have the performance information, like when an interaction has finished, users need in average 200 seconds of work in a document before requesting a new storage, or that the web server needs 100 milliseconds to process the request, it can process 10 per second, or that the application server has 2 computing resources and its execution takes half a second, or that the database needs 400 milliseconds. So this is information of our system, and if we are using UML, we don't know if we can represent this information in the diagram, in the diagrams. So for including this kind of information and having a complete UML model that also represents the performance information, we need to extend the capability of UML language. Maybe you have seen in the previous block the structure of diagrams in UML. You see them again in a different way. So the UML has behavior diagrams and structure diagrams. Maybe you know from a structure diagram, the class diagram is quite famous. Deployment diagram. From the behavior diagram, activity diagrams and sequence diagrams are the two we have seen so far in the example. And there is another kind of diagram that is called profile diagram. That this profile diagram is not used to represent a system as the rest of diagrams, but is used to extend the capabilities of the rest of the diagrams. So if we need to represent a system and the UML language does not have enough capability, we can create a profile diagram to extend the capabilities of the rest of diagrams. And there is one of these profile diagrams created for performance, to represent the performance information. It's a standard proposed by the OMG, so same people who create the UML. And it's called a UML profile for modeling and analysis of real-time embedded systems. The UML profile for Marte. So this is the profile we are going to use today to represent the remaining information, like the execution time of the activities, the number of users in the system, the think time, the probabilities of going to one activity or another. So everything that using the plain UML, the vanilla one, we cannot represent, but we need it if we want to study the performance of the system. So in a profile, when we create a profile, we extend the UML classes. So not the classes in the class diagram we create, but the classes in the UML language itself. And we extend them using stereotypes. And a stereotype will have properties that are similar to attributes in classes, and we call this property tags. And a profile provides these stereotypes that extend UML classes. We can add more information to classes, and it's like a kind of UML package. The profile also defines to which UML elements we can apply these information of the stereotype. So concretely, from the Marte profile, there is a link to Marte in my Moodle. It's a quite long document, but we are going to use only the non-functional properties notation, the library, and the generic quantitative analysis modeling, which is the profile, which are chapter 8 and 15 in the document. I think it's also specified in my Moodle. Like, it's the link to the full document, and it says in which chapters you can concentrate. So the profile defines the stereotypes and uses the data types in the library. So when we have a model, this model represents our typical system when it has also already the authentication, the signature server. So process submission in the web server, then application server, then there is a decision going to the signature server, the authentication, or going directly to the database. I use this instead of the one with 3 so we can see how to represent the probabilities. Because in the original one with 3, would not see how to add the probabilities in the UML model. So when we have a UML model, we will apply the profile, and the profile uses the data types. And this is the package representation. We have our model, and we will apply some profile, some part of the Marte profile that imports some data types. So which parts do we need to add to our UML model? When we saw the queuing networks, we saw that it was important for us, for the performance analysis, the arrival of elements, the service time of each service center, the population that will execute, the characteristics of the queues, and the routing. So when the job leaves one server and can go to more than one, how is their routing? And we saw how to model this probabilistically, and now with UML we will continue. So the same kind of routing probabilistically. So let's start with the stereotypes. You will need to know how to model 4 concepts, and there will be 3-4 stereotypes for them. Like the service times, the probabilities, routing, the workload of the system. So if it is open or closed. If it is open, we have some arrival rate. If it was closed, we had population and sometimes the think time as well. If it was interactive. And the number of resources. We were saying that our application server had 2 resources. And as an extra, we will see how to put the performance requirements. How to represent as well the requirement, like the system should be able to answer in less than 30 seconds in average. So we start with the requirements. This part on the right of the slides are screenshots from the Marte document. So you will find a figure where this is defined, and a figure where the stereotypes are defined, these 2 chapters. And there is a stereotype called GA scenario. GA comes from generic analysis scenario. And this stereotype has some tags, some properties, and one of them, 2 of them, response time, which is a duration. So if we have as the requirement the system execution shall be complete in less than 30 seconds in average, we have represented our system. We can add this stereotype this to the whole system as the execution scenario. Say that I want the response time, and we will represent this. This is in the profile, and as type of duration, and the duration is in the library. So we attach the information like this is going to be a GA scenario, the stereotype, that is The stereotype names are between these kind of quotation marks, willets. We use the attribute response time, because the requirement is the system execution should be complete. And now we have to represent less than 30 seconds in average. And here we can put a duration. We go to the library, to the definition of the duration, and it's defined like this. Duration. It has some attributes like units, clock, precision, worst, best, and it specializes from a real value that has a attribute value that specializes for common type. So let's see how we can represent these 30 seconds in average. This 30, we will use the value attribute of the real. So like response time value 30. For seconds, we have here the attribute unit, that is time unit kind, and I will show later the possibilities. So far, we'll use unit and we will see which is the value we put there. In average, this duration specializes from the real value, that specializes from common type, that has some statistical qualifiers. And these statistical qualifiers, one is mean. So there are maximum, minimum, mean. This profile is quite rich, because many people have put information that they usually require to represent their systems. We are going to use 4 stereotypes and 3-4 tags that I'm pinpointing which ones, so you don't need to study all of them. So but look at the slides, because if you look at the profile, you will find like 200 possibilities and see which ones are highlighted. So to say that it's in average, we can use the statistical qualifier mean. And source, like this is required. Source kind. And these are these 4 types, like required, it has been calculated, it has been measured, or estimated. And for the requirements, we can use the rec. So we have to define still the unit. The unit kind is defined in another image in the profile. And we have units like S for seconds, ticks, ms, like 4 milliseconds. We have the base unit, the second, and the conversion factor 1000. So if it is less than 30 seconds, the unit S. And with this, we have defined this textual requirement in the UML language. UML using the Marte profile. So if instead of the response time requirement, we have a throughput requirement, in this GI scenario, before we use the RESP-T, and there is also a throughput. So we would create GI scenario, throughput, and this is a frequency. So the frequency was defined. It was duration, frequency. Unit, frequency kind, precision, and then it also you put a value for the frequency. So for the requirements, we are going to use the scenario, stereotype, and the RESP-T tag or the throughput, depending on which one is our requirement. Now to specify the service times. So for instance, our web server needed 100 milliseconds. So to process a request, the process submission operation needs 100 milliseconds in average. There is another stereotype called GA step. We consider that this is all the scenario, execution scenario, and these are the steps. So first step, second, third optional, and then the last. So, and this GA step specializes from the scenario, and the scenario had host demand. So the way we will specify the time that our activity needs to execute, stereotype GA step, and then we will take host demand, which is a duration, so in the same kind as the previous response time. The duration had a unit, the value, statistical qualifier, and source. So the value 100, now the unit milliseconds, now our unit kinds. If it still needs to process a request, the process submission needs 100 milliseconds in average, we use the mean. If the information said the process submission needs at most 100 milliseconds, we could use the max, or at least 100 milliseconds, we could use the mean. And now as source, not required, because these are the properties. I wrote est, like estimated, because I didn't want to assume that we had measured it in the system. But if we are measuring it and reporting to the UML diagram, we can use miss as well. So this, you are free. So for the service times, we will specify them using the stereotype GA step. And the attribute host demand, which means that it demands, this step demands from its host 100 that duration. Sometimes we had in our system that when it entered some activity, it iterated. So it's like when it executes the process document, it executes it 4 times. This GIA step has also an attribute called rep, for repetitions, which is a real value. So here is not written, but iterations. Of activities. We can use the step with the rep, and we will see also another way later using probabilities instead of the repetition. Now, how to specify the routing probabilities? In the first day, we had in our example that the users only request to sign half of the documents, or 70% of the documents, not all of them. So how can we represent in the UML that this option is taking 70% of times and this 30%? It's something important for the performance, and the plain UML does not allow. And people who did the Marte needed it, so they propose a way. So still in the GA step, there is a prob attribute that is a real. So we'll put the attribute GA step with probability and the real, can put it in the arrow. And so we'll put in both arrows, one, like 70% of documents, probability, 0.7. And we remember to put the 0.3, the other. So for the probabilities of routing, we will use the stereotype GA step. With the tag prob. What else? The workload. Let's represent that there are 400 users, and when an interaction has finished, user need in average 200 seconds. This is a closed workload with some population of 400 and think time. So there is another stereotype called GA workload event in the profile that you can specify the pattern. And the pattern is of a kind arrival pattern. That some of the options are open or closed. So we put the workload in the initial node for convention. And we say that this initial node is extended with the information of GA workload event, and using the tag, the pattern, that is going to be an arrival pattern, and the data type arrival pattern can be two of the options are closed or open. And Marte also defines periodic, aperiodic, sporadic burst, but for us, at most, we will use closed or open. So in this case, it's closed, and the close is of type closed pattern. And the closed pattern is defined in somewhere else, in another figure, and it has two attributes, population and external delay. So in this case, we have population to 400 users, and the delay will be 200 seconds in average. So population 400, it's an integer directly, and the external delay a duration, like the response time. So for the external delay, we put the value, the units, the statistical qualifier, and estimated. So the value 200 seconds, value 200, the unit seconds, the statistical qualifier in average 200 seconds, so mean. If it were at least 200 seconds, then it would be, instead of mean, would be the minimum. So with this stereotype, we can represent in UML the performance information about the closed workload. So we will use GA workload event for representing this, the pattern tag, which will be, in this case, will be closed, and then the tags population and delay. If instead of closed workload, we had an open workload, so we have the frequency with which user arrive, like this. The arrival rate of user request to the system is 50 per minute or 3 per second. We will use the same GA workload event stereotype with the pattern, arrival pattern, in this case open. And the open has the attribute arrival rate, which is a frequency. So if we have an open arrival rate, we will still use the same GA workload event stereotype, and with the pattern tag, it will be open, that in turn this open we will use the arrival rate. Attribute. Now, number of resources. So our application server has 2 resources. It could be an option to say, I'm going to put in this swim line that there are 2. But it seems better to use the capabilities of plain UML first to define the resources. And this is the deployment diagram. So if we create the deployment diagram for each the elements, like the web server, the application server, the signature authentication server, and the database server, we can set it here that this is 2, not in the swing line that this is a resource and the resource has 2. So we use as much of the standard plain UML as we can, and then just in the remaining part we add the profile, the information from the profile. So how to say that there are 2 servers for the application server? There is a stereotype called execution host. So actually there are stereotypes called resource and scheduler and computing resource. But if we go as precise as we can till the end, we say that this is an execution host. And we use the attribute resmult, resource multiplicity, which comes from inheritance from the basic, but at least we define that is. Yeah. So for the number of resources in the node, in the device, first deployment diagram. And then in the node, we use the stereotype GA exec host, and we use the tag from this stereotype resmult, resource multiplicity. Like this. So our application server has the stereotype, resmult, and integer. In this case, 2. So now let's 11:07. Okay. Now we are going to see how to do this with a tool, with the Papyrus tool in Eclipse. So we can have a 10 minutes break, and after the break we will use these stereotypes using the Papyrus. Okay. Now in the second half of the lesson, we will see how to apply these stereotypes using a tool, and we will use the Eclipse Papyrus tool. So in our initial activity diagram with the 3 steps, we will add the information about the execution time of each step using the GUIA step and the host demand for each of the steps. And we will add also the workload event with a close arrival pattern with some population and some external delay. So if we do this in Papyrus, this example, 3 servers, and you will see this workload event that comes automatically, because if you click in the initial node and you go to the profile, you will have a list of stereotypes you can add to the initial node. Well, you will have a list of stereotypes once you have installed the profile. And how to do this? Go to the first step. If you don't see any stereotype, go to the Model Explorer view. If you don't see the Model Explorer, you can like Model Explorer from here, and you go to the root, and in the properties of the root, so you go to the root, then you go to the properties view, and the properties of the view has 4 tags. In the profile tag, you click on apply register it profile. I think that you cannot see much. I'm going to repeat this using also a plan B. This like the previous lesson, share my screen also in Zoom, so you will have more clearer view. I don't want to share the workspace, the Eclipse, so I want to share all the desktop, which this is the desktop I want to share, because there will be pop-ups. Okay, I hope that now you can see better the actions. So when you get a new activity diagram that we can, the same as can create, let's see. New papyrus model, a UML, somewhere, and you click on I want to model an activity diagram and I want to model a deployment diagram. So now you will see the activity diagram or the deployment. We start with the activity. Let's create the most simple system, an initial node, an action, and a final node. Now we create the control flows from the initial to the action, from the action to the final. So if we want to define the workload of the system, will be in the initial node, and we will click on profile and check and add the stereotype. But if we do it like in the beginning without any initial step, we try to add some stereotype and we will find the list empty. So we have to go to the Model Explorer, and in the Model Explorer we click on the root, then we go to the Properties view, and in the profile we apply our registry profile, and we apply Marte. And Marte has a lot of components, and in this course we need the analysis model. Actually the sum, we could even remove it. Clicking OK. Now we are applying this profile, which means that if we go to the initial node, now in the applied stereotypes, we will see the list of stereotypes we can add. And we saw that we will use the GA workload event to define our workload. The GA workload event, as we saw first in the diagrams, had an attribute called pattern, and we can define from the pattern the values. In the opaque, our activities, we will apply GA step to define the host demand. So GA step, apply GA step, and then we have the host demand, which is our real. I click on host demand. Oops. This is taking us strings instead of values. So if in the 3 activities example, the process submission, process document store info, then we have this kind of expressions. So host demand, the duration 0.1 seconds, and so estimated. And I have not written the stat queue min, but I should have written it to be completely clear. This, the workload event, has a pattern that is closed with a population that is defined as a variable that will get later a value, and the external delay 200 units. What else? Probabilities, there are not here probabilities. Number of resources. The number of resources is in the deployment diagram, so create one node for each one. And the application server. So we have used the GI exec host instead of logical resource in this model. And pool size and resmult. We say that this had a resmult and it should be somewhere. The default is 1. We can put, we have 2 elements of this. In these 4 sessions, you are free to choose logical resource or execution host. So there are some difference about which kind of resource we are modeling, but since in the specification you will get is not completely clear if it is the CPU directly, the physical element, or it is somehow logical at some level. You can use any. So if the previous hour we saw how to use the execution host and rest mode. So I recommend to go straight with this because you have slides on how to define the number of resources there. But if you want to use the logical resource and the rest mode or the pool size, it will be as a So this is how the stereotypes we will have. And we have added in the UML everything that we needed to create a performance model. So some part of the UML already represented it, like the control flow, the arrows between activities. And the rest of parts we are adding them through the profile. We have everything that was necessary in our queuing network to compute the expected utilization of resources, the expected throughput, the expected response time. So there are tools which do this. And from the UML, you can get this kind of results. And I have one of them installed, not this, DICE simulation tool. And choose which is the scenario we want to execute. And there is here a variable. Before, when we saw the workload, it was defined like 200 seconds waiting, and the population was $1 pop. And I said, this is a variable. Well, we can define variables. This is tool specific. This is not general from Papyrus. Now we are using the simulator of. And we can run this, save everything. And we can check the performance results. In this system, we saw in the second lesson, using the operational law, that the utilization of the web server was almost 20%, 0.19. The utilization of the application server was 0.49, and the utilization of the database, 0.78. I have written this while in the beginning of the lesson when the microphone didn't work, but I took the previous slides. So, and from this simulation, directly from the UML, you can see that the response time is 2.60 seconds, the throughput of the system 1.97, and the resource utilization of the web server 19.7%. quite similar. The utilization of the application server, 49.19, was with our operational loss we saw 49.2, and the utilization of the database was 78.9%, and we got in the second lesson 78.8. So this is when the designers don't know about how to compute the performance, or they don't need to know because they are specialized people, but they know how to represent this in the UML. So then the next community can get from, if they speak the same language, can get the information from the UML and create this kind of automatic transformations to performance model and performance evaluation. So in the results also in the slides, maybe it's not exactly the same numbers because they come from another evaluation I did some time ago, and the simulation also finished with some accuracy and some errors. So in this time it finished with 19.68, and in the most recent it was 19.70. So it is the same system, the one I simulated and you can find in the slides. To add the probabilities, so if we extend our three activity system with the signature server, we will need to add the signature with, let's assume 0.5 and 0.5. So if we go to, you can represent this, and in the control flows, we can put the stereotype yeah step in the control flow. So clicking on the arrow, and you can add stereotypes. And I already added the yeah step, and I put the probability of 0.5. So the other alternative should have also 0.5. So adding in this way, we can also add the information for the routine, and we could simulate this as well. So we have this information from the system, the workflow of activities, and with the performance information. We can see how much this upgrade of the system, how much it will affect the response time, the utilization of resources. So after some time the simulation finishes, and we obtain our results that now the response time is 9.63. Before the authentication server it was like 2.6. And this, if you remember the numbers from last session when we used the queuing network to evaluate this directly, was more or less in that range. And the utilization of the authentication server is 95%. So now our users are spending 9 seconds of waste time, before only 2. And you may think that this is a reasonable response time, who knows, depending on the requirements. So if response time 9 seconds, if the requirement was less than 30 seconds, we are still safe. High utilization, well, we could think about doing something with the authentication server, and the others, maybe we are still satisfied. And with this kind of model-based analysis, we can also check how much little variations affect our system, because this kind of 0.5 want to sign and 0.5 don't want to sign, maybe we don't have this information very precise. We are estimating something. So maybe instead of 0.5 is the 0.7. So we will change, instead of 5 and 5, we will put in the GIS step the probability 0.7 and 0.3, which is variation, but maybe it's reasonable. So I cannot say that it's 0.5 for sure. Maybe 0.5, between 0.5 and 0.7. So this diagram I change. I changed the value of the probability. I think in the now probability is 0.7. The probability of signing the document, and the other not signing 0.3. So if we simulate this, we can obtain as performance results that now the expected response time is 78 or 78 seconds, which, if our requirement is 30 seconds, means that we will not satisfy this. If the amount of users that will ask for the signature is 0.5 or 0.7, well, we don't know at this point, but when we deploy the system, we can, if something is not working, we can see what is going on, or if the users start testing it before the final deployment, or if we want to deploy a robust system. It's like, okay, I think that is 0.5, but I want to accept until a probability of 0.8. So in this case, you would feel that the system is not correct. So we have to do something with the authentication server, because now the utilization is at 100% and is delaying everybody. So if adding a more powerful server there, or trying to balance the load. And these are performance measures that indices that we can get quite in the design time. So the information we are using it's not about the code. It's our estimation of execution times. So even if these results will not be exactly the ones that will be experimented in the system, doing this phase at design time helps to the ignoring phase. So we had performance specification, at least we are doing what we can do at this phase. So we arrive with some confidence to the deployment, and we may fail, but the range of failure will be reduced in some way. So these are the performance results. And let's think now about another extension of the system. Somebody asked the first day, what happens if during the return the web server creates a page or something? It's not like it only executes in the beginning, then it goes to the application server, then to the database. When we saw the sequence diagram, this was like, what if the returns are not like pure returns, but process and then here create something before returning to the user. So in this case, if we are software designers, we can see that I can model it easily. So it will go to the web server, application server, authentication server, database server, then it will do some other operation in the web server, and then it will finish. And I put here the amount of time I think it is. So like here, like 200 milliseconds, and I can reevaluate. this example was nice, and I waited to the last part of these sessions, this block, because so far, if you have studied the previous lessons, you can feel that you can create the queuing network directly. And now, like, once I know why I should do this, because I take more time changing the probabilities of the attribute in the stereotype, or defining that there are 400 users and the close pattern and this, than using JMNT and create it indirectly. So we saw that the queuing network of this part was quite, so where the users, they went to the first queue. From the first one, they went to the second. From the second, they could go to the authentication, or could go directly to the database. And from the database, they came back. Now, if we want to add this little addition in the UML, it's not so little in the queuing network. So there is necessary some expertise to be able to create a queuing network that behaves as we expect with this. Because the direct way of, if the web server has to execute something, so there is something more to execute, I can put here another queue and then return. But in this case, they are not using the same server, while it affects the performance that the server is the same one. So how can we model this? We can think, I will make it execute here also, and then I allow them to finalize. But this is not modeling what we expect, because in this case, somebody can start and with some probability finish only after this. So changing the queuing network to represent this little extension is not so straightforward. Actually, this could be a way, and we need to change the class of users twice. So we could say that after finishing in the database, I change from black to red, and I come here. And this will execute and will differentiate if it is black or red to see if it takes 100 milliseconds or 200 milliseconds. And when it finishes, if they are black, they have to go to the application server. And if they are red, they should restart. But they should not restart as red, or then they will do always like this. Then at some point, I have to change them to black again. So, like this. Web server, after the database, there is a switch. Change the class of the job. Executes concurrently with these ones. But when they finish, we can also differentiate by class. And say the second class, now it becomes again the first class. So it's not so easy to do these changes, when in the UML it was like natural way for the software designer. Like, okay, there is an activity in the web server, I add another activity here in the swimline of the web server. So that's the final comment of this block. Modeling with UML, even if we know now something about queuing networks, may be still more easier for us. So this is all about this block. I hope you have enjoyed it, and now when you have performance requirements, you don't directly ignore how to behave about the performance and wait until the end to check if everything went well, but you study something about the performance during the coding, the design, the analysis, and you have some quite a your toolbox is well prepared now. So you know how to use operational laws, you know how to create queuing networks, and you know how to even represent this information in the UML that you can communicate with other people who are experts, who are also interested in performance, and maybe they use another language different from queuing networks, but in the UML can be the de facto language in which everybody speaks a little.
Camila asked the question in Slack.
Ah, okay. Thank you. Will there be some step-by-step explanation of modeling in Eclipse posted in my model? I didn't, if I had remembered to record this, I would have done it. Sorry for not recording the Zoom with the details. Yeah, I can, the main part is to the newest part is to apply stereotypes with Papyrus, I think, because after you have the profile applied, creating the actions and the initial nodes and final nodes, straightforward for designing, and then creating the stereotypes. We could have some tutorial, yes. I think I'm not going to record it because the Papyrus tutorial explains it, how to do all of this. But to give some help, I can tell you that for the assignment, you will not be required to be the expert in Papyrus because the stereotypes, you can add them as annotations. So clear text as I show it here in the slides. Let's see, like this. So instead of adding inside the activity the stereotype, you can show like this, like a comment. Actually, because in that way, it's easier for me to evaluate that you have put the stereotype. Otherwise, it's inside the properties view and it's not graphical, and I cannot know in the PDF if you have added the information correctly. So in that way, you don't need to be expert in Papyrus. Actually, there are several UML modeling tools, and I don't want to force you to know this one in this block. I hope that this answers somehow your question. So no step-by-step explanation, but it will not be required to do the model in Papyrus using the stereotypes. Okay. So see you on Wednesday. So Wednesday I will release the assignment. There will be like at least 15 hours or maybe 24 if I reach to release it on Wednesday at midnight until midnight, the next day midnight. And I will be answering from 10 to 12. So at the slot that we have booked for the sessions, is so far the only one I can guarantee that I will be in front of the computer for this. And during the day, when I see messages or other questions, I will also answer them. But then it will be a best effort. when I find time, I will look at the questions, while from 10 to 12, it will be dedicated for this assignment. Okay. It has been a pleasure. And see you on Wednesday, or if we don't see each other, good luck with the assignment and with the rest of the course. Bye.